Welcome back to the part B of lecture 5, and we are going to talk about that how we compare two models. In fact, we are going to talk about how we compare multiple models. Now, in this lecture, we will start with three possible models. Now, one is model 1, which is miles per gallon as a function of beta naught plus beta 1 times weight plus epsilon. Now this is one model with where you have essentially two variables. So basically weight, you are modeling miles per gallon as a function of weight. Okay, so you have weight on one axis and miles per gallon on the other axis, and you are modeling as a function miles per gallon as a function of weight, and that is what you are going to test. Next model is function of weight. This is already in the part of the model 1. This part is same as model 1. In addition, now you are adding horsepower. Okay, you are adding a second variable, horsepower, second independent variable or second feature, horsepower, in the model, and this is your second model. So it is going to be something like this, like on one axis you are putting weight, in one axis you are putting horsepower, and in one axis you are putting miles per gallon. Okay, so this is the second model, and the third model is you are considering horsepower and the horsepower square. So that means it's a 2D model, but you are engineering a third axis, horsepower square, along with horsepower, and putting miles per gallon on the third axis. So basically two-dimensional data with the engineered feature, you are putting it in the 3-dimension. Okay, now what we are seeing is interesting stuff, that we are seeing that if you look into, carefully, just a minute, let me just clean it up a little bit. Okay, so now if you see carefully that these are the estimates. Okay, these are the estimates of beta naught. This is the estimate of beta naught, and this is the estimate of beta 1. So this is my beta naught, this is my beta 1, this is the standard error. So estimate divided by standard error will give you the t value. Similarly, minus 5.344 divided by 0.559 will give you negative 9.559. Okay, now these values are in absolute sense quite large, definitely more than 3 sigma, plus minus 3 sigma, and you see the p value is very small, it is rounded off to 0. Okay, so that means this weight has a significant effect on the miles per gallon. Similarly, if you look into this model, that it is beta naught, this is beta 1, and this is beta 2. Now what we are seeing, that the estimates, these are the estimates, these are the standard deviation, and these are the standard deviations, and then these are the t values. And here also we see the p values are extremely small. The t values are very, in absolute sense, quite large, plus minus 3 sigma, far away from 3 sigma. So all these parameters are non-zero for sure. We can say that these have significant effect. So horsepower and weight does have a significant effect on miles per gallon. And then final third model, that what we are seeing is interesting, is these are the estimates of beta naught. This is beta 1 and this is beta 2. This one beta 2, this is beta 1. These are the standard error. and t values are very significant, and the p values are so small they are rounded up to 0. That means horsepower and the quadratic effect of horsepower also have a statistically significant effect on the miles per gallon. So based on these model, we can do all these inferences. But if I have to compare the performance of the model, which model is a good model in terms of predictive accuracy, how do we compare? So the first thing is, so naturally in a predictive model, you have to say which model. Main goal is to come up with a model which will give you a very high predictive accuracy. Now, if you want to come up with a model which will give you a very high predictive accuracy, then you have to compare between the models, and hence we are saying that how to compare the two models, or in fact more than two, we can go for 3, 4, 5 many models. So the next we will come with the concept called root mean square error. The main purpose of predictive model is to make accurate prediction. So this is the main purpose. You have to make an accurate prediction. That is the main purpose, and the main purpose of this course is to develop a predictive model which will make accurate prediction. So we can compare them based on their predictive accuracy. If the main goal is to make an accurate prediction, so we will just compare the two models based on their predictive accuracy. The model which will have a better predictive accuracy, that will be better. Okay. So what we do, the first thing, natural thing that comes in our mind is you take the actual observed, and y I hat is the predicted value of y. What is the difference between them? Square them up, take an average of that, divide that. So that is mean square error, and then square root of that will give you the root mean square error. Sometimes if you vectorize it, you get to write it in this way. Okay. These are all in vector terms, and then divided by n, and of course square root of that. So what root mean square error is one of the extremely popular measure to calculate or estimate the predictive accuracy. And then as if between the two models, the one which will have a lower root mean square error, of course we will choose that error as the root mean square error. Okay. Next, there is another popular measure is called coefficient of determination, or R square. This measure is also extremely popular. Let me explain you what this measure is. This is basically 1 minus sum of squares of residual divided by sum of squares of total. What is sum of squares of residual? So you have the predicted value and you have the original value. So original value minus predicted value square and total sum. So that is sum of squares of residuals. And then you have y bar. Y bar is just average over all the yi's in your data, overall yi. So if you just take subtract that from all y's and then square it and take the sum, that is total sum of squares. So this will give you total sum of squares. And what is sum of squares of regression? So basically predicted value minus y bar whole square, and then if you just take the sum over that, that will give you the regression sum of squares. Now carefully you see, I'll try to draw a picture, and so that you get a a slightly better sense of what is happening here, let me just give you a sense of what is happening here. So suppose you have 1x and 1y, 1x and 1y. So it's a simple, simple straight line model that you are trying to fit through the points. So effectively all values on y-axis, that is where you see the values. I mean, if I just project all these values on the y-axis, these are the values. Then y bar, it will be somewhere in the middle, the average of all these values. Now, for a particular x, you did a prediction. Suppose this y was here, that is where you have observed the y, but your prediction is here, right? So naturally, let me take a little bit different color. Okay, so this is suppose this is the predicted value. So the predicted value is yi hat, and this is the original value. Okay, here you have the original value. So the original value is here, yi. So naturally, yi minus yi hat is the residual. Yi minus yi hat is my residual. And how much? That means this residual is the residual that is not being explained by the model, right? That is the variability that my model cannot explain. That is the part of the variability in the entire data that my model cannot explain. Whereas yi minus y bar whole square is the total variability that you have in the response y. Okay, the total variability that you have in the response y. Now you are taking the ratio of the two. So this gives you a sense that how much variability my model cannot explain with respect to the total variability. Okay, and then if you just subtract that from, then this must be a value between 0 and 1, and if you just subtract that from the 1, that gives you that how much variability of my model can explain how much variability of the response. Of course, you higher the R square, better the model predictive accuracy is. So of course, the model with the better higher R square, we will choose that model. Now, R square is a proportion of the variance of the target variable that is predictable from the feature variables. So that is extremely important concept. So R square is a proportion of the variance of the target variable that is predictable from the feature variable. That is the concept that R square is trying to capture. Now I am going to tell you a result without explaining the proof and all, that for ordinary least square estimator, sum of squares of total is equal to sum of squares of regression plus sum of squares of residuals. So this result is only true for the OLS estimator. This result is specific to OLS estimator. For other estimator like Bayes estimator, lasso estimator, or bootstrap estimator, this result is not necessarily true. You have to be a bit careful about that. Now naturally, if you see this result kind of gives you that R square to be between 0 and 1. This result that typically we know in the popular context of analytics, that R square has to be always 0 and 1. Yes, R square always has to be 0 and 1, but it is true only for OLS estimator. Okay, and it is not necessarily, this result may violate for other kind of estimators. Okay, next what we will talk about is something called adjusted R square. So in the least square regression, what happens that if the R square increases with the number of feature increases in the model. So in the model, if you keep adding the number of independent variables, or if you keep adding the feature variables, then what happens, the R square keep increasing. So R square alone cannot be used for comparison of the models with very different number of features. So in order to solve this problem, adjusted R square was proposed, and what we found that adjusted R square is basically 1 minus R square times this constant, that this coefficient kind of thing. But if you notice this, if n goes to infinity, that means if you keep increasing the number of sample in your data for very large samples, for a very big data, this will go to 1. This coefficient, this part n minus 1 divided by n minus p minus 1 will go to 1. If this go to 1, then effectively adjusted R square will be approximately equal to R square. So if for very large data set where p is reasonable size, that adjusted R square will be same as the R square. P is the number of feature in the model and n is the sample size. Next, I will talk about AIC information criteria. The idea about AIC information criteria is being founded in the information theory. Now, AIC is defined as 2p minus 2 times log likelihood evaluated at MLE, where p is the number of features and L beta had given y and x is the likelihood function of the regression model evaluated at MLE or OLS estimator of beta. Now, given a set of models, our preferred model is the one with the minimum AIC value, because we want to minimize remember that for the set of parameters where the best choice will be when the AIC is minimum, given the definition. One result, it's sort of, I'm giving you as a, try by yourself, that show that OLS estimator of beta is also maximum likelihood estimator for standard regression model that we have discussed so far. So if you can take that model and OLS estimator of beta and the maximum likelihood estimator of beta turns out to be exactly same. So can you show that? So it's a small theory problem to solve. It's a theoretical practical exercise. Similar to AIC, there is another information criteria called Bayesian information criteria. Like AIC, BIC is also founded in the information theory. Okay, so BIC is defined as p times log n minus 2 times log n of L beta hat given yx. So this is same like AIC, and in AIC what you had 2 times p. This is typically known as the penalty of AIC, and this is p times log n. So some people do like BIC over over the AIC, because Bayesian information criteria sort of make a balance between the number of samples in your data set and the number of features in your data set. So BIC is slightly preferred over the AIC, but honestly, that does not make much of a difference. What my experience is, they are technically in a all practical purpose. When you will do data analysis, generally they don't violate each other. So where is the P is the number of features, and N is the sample size. So given a set of models, our preferred model will be the one with the BIC value, minimum BIC value. All right. Now I am asking you this question. Pause your video for 5 minutes and think about that, which out of these three models, which model you would like to choose and why. So pause your video and maybe you take 5 minutes and think about it, that which model would be better and which model will be we would like to choose out of these three models that we have discussed. I believe now you have found the correct answer. So let us try to figure out the answer. So based on RMSE, out of three models, if the ones we will choose which has the minimum RMSE. So based on RMSE, if the first one has 2.95, the second one has 2.47, and the third one is 2.93. So out of three models, we will prefer the second model. Okay. So based on RMSE, we would prefer second model. Now let us look at the R square. We would prefer the model which will have a R square bit higher than the other models. Now for the first model has 0.75, second model has 0.83. So second model is better than the first model because R square is higher than the first model, and the third model is 0.76. So out of these three numbers, again R square for the second model is higher. Okay. Now let us look into the AIC. AIC, minimum the AIC, better the model is. That is the criteria. So what we are seeing that the first model has AIC value 166.03, the second model has 156.65, and the third model is 167.6. So we would prefer the second model again based on the AIC value. Let us try with the BIC value. Again, if the BIC value is minimum, we will choose the model which has the minimum BIC value. So based on the first three BIC value, 170, 162 and 173, obviously 162 is the minimum, so we will choose the second model over the first and third model. Now adjusted R square and R square is similar, so higher the adjusted R square, we will prefer that model. And out of these three models, 70.74, 0.81 and 0.74, 0.81 is higher, therefore we will choose adjusted R square compared to the adjusted R square 0.81 for model 2. So based on all five metric, what we found that model 2 is better compared to model 1 and model 3. So that is how we generally choose the best model out of the all models that we are considering in our basket of models. So in the next lecture, we will try to understand the complexity of the models. So we'll stop here now and see you in the next video.